Chapter 25, Part 1, we are going to look at confidence intervals for paired samples. So in Chapter 25, we looked at two independent samples. So we looked at like men and women. We said that a person could not be in both groups at the same time. But what happens if those samples are dependent? So in this chapter, we're going to focus on samples that are dependent on one another. So this is sometimes called paired data, and this can arise in many ways. One of the most common ways is to compare subjects with themselves before and after a treatment. Since the groups that we look at are not independent, what happens in the first group will impact what happens on the second group. They depend on each other. We are going to focus on the differences between the two groups. Now, there are still there's 5 conditions now, and a lot of them you'll see are quite similar. Okay, the first one is that we must have randomness. So we need to have those random samples, just as we've seen in the past. The second condition is again that your samples must be less than 10% of the populations. Okay, we're still going to look for nearly normal. This time we're going to look at the differences between the two groups. So I'm going to say that the differences must be nearly normal. Now, those three should sound very, very familiar. They're almost the exact same as what we've seen in the past. These last two kind of change depending on the data. So if you're given two groups and you think that this data is dependent, so maybe it's looking at some kind of experiment and I take heart rates in the beginning and then I take heart rates, after some kind of medication, that would be dependent data. The data is coming from the same group of people. Then the next condition is that we must have paired data. Okay, when I think about paired data, I'm going to make just like a quick little chart over here. Most of the time you'll see your data is given to you in 2 columns like this. For simplicity, I'm just going to call this X and Y. And I might have like 10, 12, 24, and then here it's 40, 44, and 50. Okay, if you think that this 10 and 40 have to go together, like those are somehow related, maybe that's, the number of hours worked in high school versus college. But if you think that their two numbers are related, then chances are that you have paired data. If you could switch the numbers around, so if I could put 44 here and 40 there, and it wouldn't change your data, then you probably don't have paired data. Okay, our last condition here is that the differences must be independent. So as I look at my table again here, going from X to Y, so let's just say that this was data for SOTO. This is how many hours I worked during a week when I was in high school versus college. And then down here we have Miss Peck. She worked 12 hours when she was in high school per week, 40 hours when she was in college. Now, although the data is paired, like this data has to stay with me and this data here has to stay with Miss Peck, once I find the differences, so like my difference was 34, sorry, you can barely see there. And then I could find the difference for Miss Peck, so the difference between 12 and 40 would be, what, 28? Okay, these differences is what I'm looking at. The 34 compared to the 28, those are independent. Just because I had an increase of 34 doesn't mean that that's impacting Miss Peck's increase. So when I talk about differences, that's what I'm looking at, the difference between those two groups. Okay, when the conditions are met, we can find a confidence interval for the mean of the paired differences. So we're really going to be focusing on these differences here. So I grew by 38, Miss Peck grew by, I grew by 34, Miss Peck grew by 38. That's the differences that we're focusing on. So what we're going to do is start with finding the average difference. I'm going to call that D bar, standing for the average of the differences. We'll add and subtract a t-score with degrees of freedom. And then I'll multiply by the standard deviation of the differences. So I'm going to call that S sub D and divide by the square root of the sample. Okay, on the next page we'll see a few examples using this formula as we go through several questions. All right, example 1 says, field workers for a health department compared driving mileage on a 5-day work schedule with mileage on a new 4-day schedule. To see if the new schedule changed the amount of driving they did, create a 95% confidence interval to look at the paired differences in mileages before and after the schedule change. So our data here lists the employee's name. So we have Jeff here. This is the miles that he drove on a 5-day work week, 4-day work week. This is his new mileage. Okay, then we have Betty, Roger, Tom, Amy, all of these guys, these are all of my employees, and then their mileage here. Okay, I'm going to start with checking my conditions. So first two I'm going to focus on are my randomness and my less than 10%. So let's see if it says anything about random. I'm not seeing the word random anywhere here, so I'm hoping that these employees represent all employees. So I'm going to say employees listed should represent all employees. Okay, there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 employees. Definitely less than 10% of all employees. Okay, after these, I recommend you stop and you think about what kind of data we have. Now, this is a great example of paired data or dependent data because there's no way that I can switch these numbers without it impacting my study. For example, these first two numbers correspond to Jeff. The next two numbers correspond to Betty. So I couldn't just switch this 2,000 with the 7,000 because the 2,000 is what Jeff did, the 7,000 is what Betty did. These two numbers are dependent on the person. So this is paired data or dependent data. Okay, because I'm looking at dependent data, what I really want to do is start with finding the differences between these values. So in my calculator, I'm going to type in all of their 5-day mileage into L1. I'll type the 4-day mileage into L2. And then what I'm going to do is find the difference here, and I'm going to put that in L3. So let's start with typing in the data we have. Go ahead and go to Stat, Edit. I already have my data typed in here, so go ahead and pause your video to give you a few minutes to type in that data. Now that you have all of your data typed in, we want to find the differences between these two. Now, we could sit here and use our calculators, or you could just do it in your head. What's easier, though, is if you scroll over to L3, and you have to scroll up so that L3 is highlighted. What we're going to do is tell our calculator to take L1 and subtract L2. So I'm going to type in here, second 1, that should pull up L1, minus second 2 should pull up L2. Okay, so far you've told your calculator, I want L3 to equal L1 minus L2. That's what we're going to put in this L3 here. I'm going to go ahead and press enter, and it finds all of those differences for me. Okay, once I have those differences, that's really what I'm going to be focusing on for the next several conditions. Now the next condition I'm going to check is that normal condition. I want to make sure that the differences that I have here, so the things I have listed in L3, are normal. So I'm going to go to my stat plot, second y equals. I'm changing this to a histogram, but I'm going to change this to pull data from L3 since that's where I have my difference. And zoom 9 gives me this weirdo histogram. And I'm also going to make a normal probability plot. Okay, it's definitely not looking perfect, but it's close enough. All you need is close enough, so I'm just going to say that these differences are nearly normal. And I'm going to include here that this was just looking at the differences, was not looking at each one individually, just looking at the differences. Okay, the next one that I need to look at, I kind of already thought about, is do I have paired data? We said at the very beginning that this was definitely paired, so I'm just going to say paired data here. And my last one, I need to make sure that my differences are independent. So do you think that the difference that Jeff had is going to have any impact on Leslie's differences? I don't think so. So I'm going to say differences are independent. That part can be kind of tricky because your data itself is dependent, right? Like the stuff we have in L1 and L2 is definitely dependent. These mileages are dependent on the person. But when we're talking about these differences being independent, we're saying that person to person, those differences are not impacting one another. Okay, my conditions are met here, so I am good to start making my confidence interval. Before I make that confidence interval, I do need to calculate some statistics, right? I need to find all of my, my mean, my standard deviation, all that fun stuff. So we are going to run our 1var stats again. Just as we've done in the past, the big difference is this time I need to make sure I'm pulling that data from L3 since I am finding a confidence interval for the differences in these pairs. So I'm going to go to my stat, calculate my 1var stats. I did L2 last, so I'm going to change that to L3 by hitting second 3. Going down to calculate. Now, when I write this, because I found all of this info for the stats, for the differences, I'm going to write this as D bar 982. And then I also can find the standard deviation of the differences, so that's my S sub D. That is 1139.57. Okay, just like we've seen with these confidence intervals before, I am also going to need to find my degrees of freedom and then also use that to find a t-score. So I'm going to use my calculator here to find those degrees of freedom. Remember that we go to stat, tests. Now this is kind of a weird part. This is still technically just called a one-sample t-test, or just a regular old t-interval. So I'm just going to look for t-interval. It's kind of crazy, but really all we're doing is the same thing as a one-sample confidence interval, but the only difference is I'm focusing on differences instead of just one set of data. Okay, my data this time is coming from L3, so make sure we change that to L3. Remember, we're really focusing on those differences. Confidence level, 1 in 95, so I'm good. So here's my interval. I'm sorry guys, I kind of jumped ahead a little bit. I don't know what I was thinking. It's been a while, you know. Spring break really got to me. I can find my degrees of freedom just by taking my sample size, which I believe we said was 11. Yeah, we had 11 employees. Subtracting 1 gives me 10 as my degrees of freedom. I can then go ahead and draw my little picture here, finding that t-score. Remember, we're looking for that middle 95%. So that means I'm going to have 2.5% on each tail. So it's going to be my t-score degrees of freedom of 10. Again, sorry, I don't know why I just completely skipped that part. Okay, so I'm doing second bars, going down to inverse t. My area is 0.025, degrees of freedom is 10. Gives me a t of negative 2.23. Okay, once I have all that, I can start making my actual interval. I'm going to write down just my formula. Again, we said to take the average of the difference, so your d bar, plus or minus the t-score, times the standard deviation of the differences, dividing by the square root of n. I now have all of these values, so we can go ahead and plug in. So I have 982 plus or minus my t-score, 2.23. I'm just making that positive again because of that plus or minus. My standard deviation over the square root of 11, since we had 11 people. Okay, I got a margin of error of 766.21, so I'm going to add and subtract that. Giving me 215.79 and 1748.21. Again, what I did earlier is I could check that by doing my stat tests, just a t-test, t-interval, data from L3, 95% confidence when I calculate. It's off slightly due to my rounding, but it's not too far off there. Now the last part that we need to do here is interpret our interval. There's a few ways you can interpret it, but I kind of like to write my interpretation very similarly to how we wrote the interpretation for 2 samples, because really what we are doing is looking at the difference. So we ran it very similar to a 1 sample t-interval, but I like to relate it back to what these 2 groups actually were. So I'm going to say that I'm 95% confident that the true average 5-day mileage is, now these are both positive, so they're going to be higher, and these are mileage, so that's in miles, I'm going to assume. So I'm 95% confident that the true average 5-day mileage is between 215.79 miles and 1748.21 miles. I'm going to say more than or greater than. I should have given you more room here, guys, I'm sorry. Is greater than the 4-day week. So essentially what we found here is that we are pretty darn sure, we're 95% confident that if we require workers to work 5-day, week versus a 4-day week, they are going to have higher mileage by about somewhere between 215 miles up to 1748 miles. Okay, let's take a look at example 2. Okay, example 2 says the table below gives the average high temperatures in January and July for several European cities. We want to write a 90% confidence interval for the mean temperature difference between summer and winter in Europe. So looking at our data, again, it's listing the cities and then the high temperature in January compared to July. So in Copenhagen, it was 36 versus 72. In Madrid, it was 47 compared to 87. Okay, hopefully you're noticing that this is, again, a great example of paired data, since these two values, right, the high in January and July, are dependent on the city. I could not just randomly switch two values here because they relate back to that city there. I want you guys to go ahead and pause your video, give this one a shot. You're going to run it just like we did the last one. So type all of your January data into L1, July data into L2. You'll find the differences in L3. Check those conditions, find all of your stats, create that interval. Once you're done creating and interpreting the interval, go ahead and play your video again and I'll walk through all of my work. Alright, here is my answer for example 2. I'm going to go kind of piece by piece here. Conditions, it didn't say they were random, so I just said these cities should represent all European cities. The 12 cities listed is definitely less than 10% of all European cities. The last 3 then, make sure that you are using the differences. So if you have January in L1, July in L2, you're finding the difference in L3. Again, you can do that by typing or scrolling up to L3 and typing in L1 minus L2. Should give you all those differences there. Don't freak out that they're negative. They should be negative because you're taking these cold January temperatures and subtracting those higher July temperatures. Histogram and normal probability plot, they're not perfect, but they're close enough, so I said the differences are normal enough. Data is definitely paired because these two numbers correlate back to Vienna, and those differences should be independent. Just because Vienna had a difference of 41 and then Copenhagen and a difference of 36, I don't think that those differences are impacting one another. Okay, the next thing I did was use my calculator to find some of these statistics. So I found the average difference is negative 36.83, standard deviation 8.66. Degrees of freedom is just one less than the sample size, so 12 minus 1 gives me 11. And then I did a little inverse t here with 5% on my tail since I have 90% confidence, giving me a t-score of negative 1.8. Okay, next up, building that model. So I took the average, so that's d bar plus or minus the t-score I just found, times standard deviation divided by square root of 12. Here's my interval. This was slightly different if you use the calculator. So when you use calculator, if you go to test t interval, data L3, just changing this to 90%. It was off slightly, negative 41.32 and 34. Here, either option is fine depending on your rounding and whatnot. Okay, the last part then is that interpretation. So I said I'm 90% confident that the true average temperature in January is between 41.33 degrees and 32.33 degrees lower than the average temperature in July. Okay, hopefully you're noticing that these paired t intervals are almost the exact same as your one t interval, right? Your one sample t interval. The only difference is that you're finding that one sample, you're finding those differences using the paired data that they give you in the very beginning.